Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Triangulation is brought to you by Cashfly at CACHEFLY.com. This is Triangulation, episode 204, recorded Monday, June 15th, 2015. Dr. Justin Sanchez and DARPA. Triangulation is brought to you by SmartThings. SmartThings lets you monitor, control, and automate your home from wherever you are using your smartphone. Right now, SmartThings is offering Triangulation listeners 10% off selected kits and get free shipping in the U.S. when you go to smartthings.com/triangulation. And don't forget to use the offer code Triangulation at checkout. And by Personal Capital. With Personal Capital, you get award-winning financial tools, unbiased advice, and a transparent view of all your investments. Best of all, it's free. To sign up, go to personalcapital.com/triangulation. And by Braintree. If you're working on a mobile app and searching for a simple payment solution, check out Braintree. With one simple integration, you can offer your customers every way to pay, period. To learn more and for your first $50,000 in transactions, fee-free, go to braintreepayments.com/triangulation. It's time for Triangulation, the show where we get together with some of the best minds, the most interesting people in technology. We sit down, we talk, and we have so much fun. And to start this off, I couldn't do this interview alone. It was too hard. It was DARPA hard. So I brought in my old buddy, Marc Pelletier, who I never said your name right in my whole life, Marc. I want to say Pelletier. You say Pelletier.
In the U.S., I say Pelletier, and
right.
In Canada, I say Pelletier.
You may remember him from that great show, Futures in Biotech, for some years on our network. We learned so much together, Marc, and it was so much fun doing that show. But Marc got a little busy. He founded this company called Aeromics that's trying to, just eliminate death from stroke. No big deal. Actually, I want to hug you, Marc. Keep up the work.
The drug's working, so we're moving forward.
That's awesome.
It's awesome. A lot of work, though. Imagine 8 years and then of banging your head against the wall in the laboratory, and then coming up with a molecule that's safe in humans. So that was the hard part. And if it failed, well, you lose 8 years of your life, right?
And I didn't know this because I know. So our guest is from DARPA, and I know DARPA because the Defense Advanced Research Projects Administration, I guess. Agency. That's Justin Sanchez.
Hi.
He is a director, a program manager at DARPA, and he's in the part of DARPA that I didn't know about. I thought, they invented the internet. Not so bad. They did they just completed the DARPA robotics competition. They really autonomous vehicles owe a lot to DARPA. But what I didn't know is there's a whole Biological Technologies Office, or BTO. I like the acronym. And Dr. Sanchez, Dr. Sanchez is at the BTO, and get what he's working on: machine-mind interfaces.
Yeah, brain-machine interfaces. Leo, I really wanted to bring on Justin because we talk about the Apple Watch has been in the news and all these wearables, and it's kind of like a new level of interface. But if you look at how we've been interfacing with computers from, in the 60s, mouse and keyboards, and then, in the early 70s, Annette Goldberg brought in the graphical user interface, and then it jumped all the way. So we had like a Windows-like operating system where we, move a mouse around, then touch in 2007 with the iPhone. All those things in common, you're interfacing with the computer where you think, you move your finger, you have an action, and then the computer responds. But what Justin's doing and has been doing, has spent his career doing, and now overseeing at DARPA, is looking for that next level. Having a brain-machine interface, how about you just sit there and think about it? Or you don't even have to think about it. The computer recognizes your brain signals in sort of a sensory loop where you just saw something. The computer said, "Oh, he saw that. Let's create an action." And you're enhancing human capabilities in a way where you don't even have to think or touch. So, this whole concept of touch on a phone this goes beyond where sci-fi has been able to envisage. its uses. So I think we should take a good hard listen to what Justin has to say and where this is going, because we're going to know where things are going here at TWIT and on Triangulation. We're going to get that little advantage of where things are going to go in the next 10, 15 years.
Dr. Justin Sanchez, welcome to Triangulation. Great to have you.
Thank you so much for having me.
We should mention Dr. Sanchez is so well dressed because he could be called by the president at any moment. You don't want to go to the White House in jeans. So this is your area of expertise. You're professor of biomechanical engineering. Who even knew such a thing? This seems like the stuff of sci-fi.
Absolutely. We've been thinking about this problem for a really long time on how we change the way that we interact with machines. Tools and machines have played a huge part in our lives for many years, right? And they change the way that we interact with the environment. And today we're having a very different conversation. As Marc mentioned, this whole wearables development is happening right before our eyes. And, we see new opportunities for how our physiology is getting outside of our bodies and doing work in the world for us. And one of the missions of DARPA is to really stay out in front and ahead of these things that are coming down the pipeline. Just real quickly, the agency was formed in 1957, 1958 era, when we found out that other countries had technologies like Sputnik, and we didn't. And the leadership at the time said, look, we need to create an agency that will create surprise, prevent surprise, and make sure, again, that we never, ever get caught off guard. And as Leo said, one of the new places that we're pushing in today is in the biological technologies. And the office that I'm appointed in actually just got started in April 1st of 2014, and we've got some really fantastic things coming down the pipeline.
I wasn't completely joking when I said that the president might call, because this is part of the president's brain initiative, I gather.
Yeah, all of the programs that I manage are in support of the president's brain initiative. And for all the people listening in today, this kind of goes back to 2013, where President Obama set out a national initiative that said, look, there's some real challenges in brain science, in health related, to the brain. And we need to get out there and develop the next generation kinds of technologies. Now, if you actually look at the acronym for the Brain Initiative, one of the key words that's in there is innovative neurotechnologies. So we're not just approaching this from hey, we're going to just observe the brain and try to understand what's actually happening with the brain. We're going to develop new technologies, new interfaces to the brain that will help to deepen our understanding. And the area that I particularly work in is this area of neuroprosthetics, or direct brain interfaces, where we're trying to develop hardware to interact with neural circuits in your head and allow you to do remarkable things like restore your memory after you've had a traumatic brain injury, or restore your ability to move after you've had a spinal cord injury, or help you get back to a normal quality of life if you're suffering with a neuropsychiatric illness. So these are some remarkable things where today we don't have a whole lot of options for dealing with those. And let's take memory, for example. If you've been hit in the head by a traumatic brain injury and you've lost that ability to form or recall memories, the best you can do is kind of go and talk to your physician. Maybe they give you some kind of behavioral therapy. The conversation today is very different than that. We're trying to say, can you develop an electronic device that would directly interface with your memory circuits and help you to form those memories and help you to recall them in the future? Again, it sounds like science fiction, but it's something that we're working really hard on, and it looks like it's really going to happen.
In the announcement, they said, this is the Human Genome Project for the brain, in effect. Why now? It feels like the time that we're already making some of these breakthroughs. The time is right now to go with functional MRIs. We have a better understanding of how the brain works. I know from family members with mental illness that we're making amazing strides in pharmaceuticals. This seems like we're starting to make these breakthroughs. This is a good time to do that. Is that accurate?
Yeah, Leo, I love your question of why now. one of the core concepts at DARPA is we answer something called the Heilmeyer questions. If you guys have never heard of the Heilmeyer questions, you should go on Google and take a look at them. And one of the questions in this catechism here is why now? Why is this the appropriate time to be doing this? And it really boils down to a couple of things. So first of all, our computing technology is getting to a point now where it's sufficiently developed where we can access large numbers of neurons, read out that information in real time, and actually act upon it. And just a brief story here. So before I was at DARPA, I was actually an academic researcher. And, I can remember many long nights in the lab where, we were trying to record from 10 neurons. And it was a struggle just to read out all of that information because our computers weren't fast enough to actually do it.
You mean 10 neurons generated so much information the computer couldn't keep up?
Couldn't keep up. We couldn't process that information.
How many neurons are in the brain? That's 10. How many are in the brain?
Yeah, there's a trillion maybe.
Jeez.
Well, a trillion. Most of those are glial cells or astrocytes.
Yeah, they don't do nothing.
Too nerdy on.
Okay.
But
one
still,
quick interjection here.
If we want to get into hundreds of neurons, right, and that's where we're at now, between hundreds and thousands of neurons, we're really pushing the limits on being able to process all of that information. And again, if you're thinking about complex behaviors, you're going to need a pretty good number of those neurons in order to reconstruct those kinds of behaviors.
Let me ask you, Justin, if you look at the honeybee, right, doesn't the honeybee only have one main neuron, and it can store enough information to be the equivalent, if it was the size of a human, to travel to a flower that might be the same distance from Los Angeles to San Francisco and back on that same neuron?
Wow.
How much information can you gather from one single neuron, and then how would that relate to the multiplexing going in with the large number of neurons?
Yeah. What this really boils down to is that idea of the neural code. So here's another really interesting concepts for the listeners out there is, look up neural code and what it means. And when it comes down to the information, extracting enough information from the brain to do something useful depends upon the function that you're looking at. So, let's say you're just trying to move your arm, let's say up, down, left, and right. You may be able to pick a handful of neurons that only fire, let's say when your hand moves up or your hand moves down, there may be a different set of neurons. And if you can observe those, you can write computer code to say, hey, whenever I see those neurons firing, it means this or it means that. When we get to more complicated functions, let's say like cognitive function or memory function, the question of how much information is in those neurons becomes much more difficult, right? And just take a simple memory like the Eiffel Tower is in Paris. Mm-hmm. It's very difficult for anybody to say in any scientific or medical realm which neurons contain that information. How fast or how often do they signal that kind of information? And even if you were able to observe it, what you would do with that kind of information. So that's kind of the level that we're on right now, is that we have some clues or some hints on how the neurons represent those kinds of behaviors. And the new programs and the projects that we're working on now is trying to understand those concepts in human subjects. A big problem with a lot of this work right now that happens in academic kind of circles is that it's done in animals, right? And you can't always ask an animal, what did you remember or how did you remember? But now that we have this opportunity that we're kind of studying these functions in humans, we can take it to a very different kind of a level.
We're talking to Dr. Justin Sanchez. He's a program manager at DARPA, the Defense Advanced Research Projects Agency, in the Biological Technologies Office, BTO. Fascinating stuff. Joining me, Marc Pelletier, who's the former host of Futures in Biotech, is a biotech, I would say, innovator himself, and perhaps is going to change your life and mine with his research at his company. But before we go on, let me take a little break. And when we come back, I want to talk about we've talked a little bit about the Heilmeyer catechism. I got a few more questions from the catechism. Who's going to benefit? What's it going to cost? What is the prognosis? How long is it going to take? But we'll talk some more about that. So you can see why this is part of the Department of Defense, though, initially, because soldiers returning from war, suffering brain injuries, loss of limbs, you could see immediate huge impact there. And we'll talk about that in just a second. Our show today brought to you by something pretty smart, too. Smart Things. We talk a lot about smart things. I got all my smart things doohickeys here. This is a way to make your house a little smarter with a Smart Things. Starts with the Smart Things hub. I mean, that's the key. The hub talks to your smartphone, Windows Phone, iOS, or Android, and then talks to the Smart Things hub. This is not going to go well if I keep building this tower here. But this gives you some idea of how many different devices, different ways your hub, you think, can I do one more? Your hub can talk to the outside world. And by the way, more than just this, because the hub also talks to hundreds of other devices with Zigbee and Z-Wave and the other home automation standards. Finally, a way to solve that Tower of Babel I was just building. To make your home more intelligent. This is the key right here. We love Smart Things. We've got 3 different Smart Things kits that we've got a discount on for you. There's the 3 of the big things people want to do: the home security kit, the energy saver kit, and the water detection kit. And we can get you 10% off any of those 3. All of them include the hub. So that's just the beginning. The hub talks to so many other things. In fact, if you go to the products page of Smart Things, you can see the list. You'll see how powerful this solution is. But we like to get you started with doing something concrete, saving 10%, getting free shipping in the United States as well at smartthings.com/triangulation. You can control your lights, your locks, your security, your Honeywell thermostat, your drop cam. It all works with Smart Things. And, it's unfortunate companies are still using proprietary systems, but Smart Things solves this. It's so great. No wonder it won the Editor's Choice Award at CES this year. Smart Things, through June 30th, 10% off their most popular kits, smartthings.com/triangulation. And you will feel pretty smart. It's so easy to do, but you'll feel pretty smart when you say, press a button on your phone and the lights turn off and the music starts playing and the windows, the curtains draw and all of that. smartthings.com/triangulation. We are talking with Dr. Justin Sanchez from the Biological Technologies Office at DARPA. Before the show, somebody in the chat room said there's a phrase, DARPA Hard. When something is virtually impossible, they say it's DARPA Hard. You're going to have to send this one to DARPA. And I think you've picked a DARPA Hard thing to do. How far have we gone, Dr. Sanchez, in using I've seen, I think, monkeys controlling things with their minds. Is that right?
Yeah, so monkeys have done it, but we've also had humans control prosthetic limbs just by thinking about it, and they can have near natural control again of artificial limbs. And if you just go on the web and look up DARPA and prosthetic limbs, you'll be able to see some of those videos. But a quick story on how this came about and how fast it happened. One of the interesting things, before I was at DARPA, again, I was academic research and I actually worked on the first brain-machine interface program. Again, as a scientist on that program, and this was in the early 2000s, so like 2001, 2002. And I remember going to the kickoff meeting for that project and people saying there that it would be 50 years before humans would have a direct brain implant and be able to control a prosthetic limb just by thinking about it. And back to that kind of the DARPA approach, or how DARPA deals with hard kinds of challenges, we can accelerate. And over a course of 5 or 6 years, we actually made that happen.
Is this guy, we're watching a video of a guy controlling an arm. There's no physical control going on here. He's thinking pick up and it picks it up. He's thinking open the hand.
So not in this example, but if you actually look up Jan Sherman and DARPA revolutionizing prosthetics.
Okay.
You may be able to find some of the videos online for that. Yeah. But again, there's great some great clips of her actually controlling the prosthetic limb.
And this is from just a couple of months ago. Solely with her mind. She's a paraplegic, has no use of her limbs.
That's Jan right there.
Yeah. In fact, it looks like she uses a chin stick to do a lot of the work she does. Was this a 60 Minutes piece? I think it was.
Yeah, there was a 60 Minutes piece on this. Quite remarkable. Yeah, she's an amazing person.
What a breakthrough, though, for her to. I think of things like cochlear implants. The advances we're making now are just truly remarkable, and it all comes with understanding something that is so hard for us to observe. The mind observing the mind is quite a challenge.
Could you, Justin, have a sort of a feedback loop or sensory loop where the electrodes don't just read the intent of the brain, but send back signals in parallel where you could actually feel it, right?
Yeah.
So you could have a prosthetic arm and feel hot, cold.
Yeah, so you can actually do those kinds of things. Jan did not have a version of the system where she could feel it, but this is closing that loop. So not only having the movement part, but also the feeling part of it. That's one of the last milestones to be achieved on the revolutionizing prosthetics program at the agency.
Wow.
So yeah, again,
take it one step further. Have somebody else feel it. Sorry, I interrupted. Go ahead.
Wait a minute. Is she controlling this with her mind?
Yep. There's an example of her. The signals are coming straight out of her head and into that robotic arm, and then controlling that robotic arm to move.
How hard is this for her to learn?
Yeah, that's a fantastic question. So she has near natural control. So the moment that we turned it on, she was able to control that arm system. And the reason we're able to do that is because of the exquisite understanding of how the motor system of the brain works. So kind of back to that President's Brain Initiative there, one of our goals is to learn as much as we can about the function of the brain, but then apply it to very useful kinds of everyday life activities. That's really where we're headed. So we just don't want to observe the brain. We want to use it to do something useful.
What are the tools you use to figure out where the loci of this are and how it's working? I mean, what do you do? Do you probe the brain?
Yeah. So she'll have an fMRI. If you can have one, you can localize where in her brain those signals are emanating from.
She's feeding herself.
Yes. So again, interesting comment on this. Jan has told me that one of her primary motivations for this was just to feed herself chocolate again. And again, for somebody who's paralyzed, this makes all of the difference in the world, right? You have that function taken away from you, and then to think that you could potentially get it back, it's life-changing, it's transformative.
Let's go back to this computer display, because I have a feeling that has something to do with the brain waves and the impulses. Let me jump to that.
Yeah, right there. So remember back when we were talking, being able to process signals just like this was really a challenge in the early 2000s. Again, there's very few people that had hardware systems that could process this kind of information. And just to give you a little bit of a reference here, if you just kind of look at those little purple lines there, those magenta lines, every time you see one of those lines, that's one neuron firing.
Okay.
And it's the firing of those neurons which contains the information about, I want to move in this direction, or I want to move in another direction, or I want to open my hand, or I want to close my hand. So what needs to go on the actual computers, we need to take those squiggly lines and translate them into control commands for the limb. And that's the really hard part. And we have mathematicians and electrical engineers and really, really smart people trying to figure that out.
So this is in effect translating the brain waves into intention.
Exactly. You're translating thoughts into action.
Can you carry that over from one patient to another, though? If you've got 100 patients all thinking, this is how I move my arm, that you could then use that to tweak for the 101th person and the 100. Is it an iterative process, or do we all use different parts of our brain?
So everybody's a little bit different, but the only indications that we have on this ability of having the codes be similar amongst individuals, that we've done some studies in animal subjects in the area of memory, where we've been able to show that one memory construct in one animal can be useful as a memory construct for another animal. So
take that to 37,000 feet there. What does that mean? Does that mean you could learn, I don't want to be facetious about this, but you could learn Kung Fu, and then, because you've learned it, I could then learn it quicker?
So we don't know for sure yet, but there are some hypotheses out there that say that those neural codes may be similar enough that a person could rapidly learn skills in a very different way. And we have this Restoring Active Memory program that's kind of looking at some of these different aspects and the fundamentals of actually doing those kinds of things.
Unbelievable. This is just fascinating.
There's.
Go ahead.
Sorry.
No,
I was going to say there's two levels of sensors where you have the sort of the non-invasive and invasive sensors, and at what point do we just go to non-invasive sensors? Do you need to go into the brain to and tap the neurons?
Mark, so this is a fantastic question. I'm so glad we're getting an opportunity to talk about it, at least with this audience here, is that we see a ramp between what's happening in the wearables domain. So again, wearables are really coming of age right now. Lots of people are using them. But the place that we struggle right now with wearables is, if you were to buy any of the ones that are on the market right now, they just get back to you with, oh, I walked 8,000 steps, or this is what my heart rate is right now. We see very little action in that space in terms of people processing that information and giving actionable feedback to the user of those kinds of devices such that they can change their life. And, we've talked to many of the device manufacturers in Silicon Valley and beyond. And, nobody's really, from our point of view, working on that. And one of the things that, I'd love to just tell the audience, DARPA is a funding agency, and we're looking for the next great innovative idea for how to solve, that kind of a problem. People can always share those kinds of ideas with us. Now, back to your question, though, is that, while we are getting into this space in the wearables market, there would likely be some convergence with those kinds of devices with the devices that can directly record neurons from your brain. But that's going to take time, right? That's going to take a few iterations of that technology to make it safe and make it deployable in a way that people can uptake in an easy way. So a little bit more time on that one.
One of the things that President Obama mentioned with the brain initiative was Alzheimer's and mental illness. It's not merely prosthetics. Mm-hmm. I guess this all comes out of understanding better how the brain works. Yeah.
So to address the mental illness issue, this is a huge problem, not only for military personnel. I think the quote is 10% of the 22 million veterans are living with some sort of neuropsychiatric illness. And again, if you apply the DARPA approach to this, you say, what's the best you can do right now? And the best you can do right now is maybe go see your psychiatrist, maybe get prescribed some medications, lay out on the couch and talk about your problems. But from our perspective, that's one step, but we want to go much deeper, right? We want to use knowledge and we want to use technology to try to solve those problems. So we do have a program. It's called Subnets. Again, it stands for a very long series of words: systems-based neurotechnology for emerging therapy. Despite the long set of words there, it really stands for a neuroprosthetic, an implantable neuroprosthetic that can be used to sense malfunctioning neural circuits in the case of neuropsychiatric illness and deliver targeted therapies directly back to those neurons in the brain that are causing those kinds of problems.
Where would you wear that?
Excuse me?
Where would you put that?
So the way that we're designing these technologies is that they're going to be fully implantable, either in the head or have components of it in the chest, and leads can be routed up into the head.
So it would sense an imbalance and attempt to medicate it or cure it.
Or medicate or modulate those neurons that are causing those issues. And some of you may have heard about a predicate kind of technology in this space. There are devices called deep brain stimulators that are used for things like Parkinson's disease. These devices are very similar to cardiac pacemakers, but instead of stimulating the heart, they actually stimulate the brain. And over 100,000 people have these kinds of devices already implanted in their heads today. The interesting thing, though, is that while those devices are out there, stimulating the brain is very different than stimulating the heart, right? The brain is an adaptive system. There's dynamics to it. It learns. There's all kinds of things that are involved there. And the devices that we have today in the deep brain stimulation realm can't contend with all of those issues. So that's why DARPA is developing the next generation kinds of devices that can, again, record from the brain, process that information on board in that implantable device, and then deliver that targeted stimulation back to the centers of the brain that may be causing the problem. Again, that technology doesn't exist. We have to develop it.
We're going to take a break. When we come back, Marc Pelletier is here. He is, of course, longtime friend of the Twit Network and the creator of the Futures in Biotech podcast. His company now is making some interesting and great strides in the treatment of strokes. Aeromics, you'll find them at Aeromics, AEROMICS.com. And, of course, Dr. Justin Sanchez, who is a program manager at BTO at DARPA. And we're talking the Biological Technologies Office, and we're talking about the brain, prosthetics, advanced ways to talk to the brain, for the brain to talk to devices, and we'll have more. I'm really curious how you learn the language of the brain. We'll talk about that in just a second. Our show today brought to you by Personal Capital. Oh, I love Personal Capital. A lot of, in fact, started right here in this very studio when we talked to Bill Harris a few years ago, and he was just starting this company. I was interested in Bill because he was one of the founders with Elon Musk of PayPal. He ran Intuit for a while as a CEO there. And, probably could have just taken it easy and said, I'm done. But instead said, I have an idea to help people, you and me, with planning for our future, particularly for our retirement. And that's how Personal Capital was born. When he explained it to me, I said, I'm signing up. I've been doing it for a couple of years now. What Personal Capital does is it gives you a free, absolutely free financial dashboard. It's kind of the starting point is just knowing what your money is doing, where it is. You enter your accounts in there. It's completely secure. You'll get a dashboard on your phone, on your tablet, on your desktop that says where your money is, what's going on. You can analyze how your investments are working, where you're spending too much money on advice from a broker or on commissions and fees. Most brokers aren't working for you. They're working on commission. They're working for they're salesmen. They're trying to get you, frankly, to trade more, to buy more, so they can make more money. Not with Personal Capital. Personal Capital's financial advisors have a fiduciary responsibility to look out for your best interests. They do not work on commission. They are not brokers. Their goal is to make sure that you are saving properly for your future, and they can help you do that. First with a dashboard. That's free. And by the way, if you put $100,000 or more of assets in the dashboard, you can also schedule a free consultation with these guys and gals, and they will help you look at your goals, your risk tolerance, your time frame, and really understand, what you're doing and if you're doing it right, and if you're sadly losing years of retirement due to hidden costs. Get rid of those hidden costs. This is all free, by the way, personalcapital.com. On your Android Wear Watch, too, and your Apple Watch, too, you get alerts. I love that. It'll say, your investments did well today, or you might want to check out the commission you just paid. Personalcapital.com/triangulation. Start today. It's free, and it is a great way to find out exactly where you stand. Personalcapital.com/triangulation. Give it a try today. We're talking about the future, but it's right now in the present. It's kind of amazing that I feel like we're already starting to understand so much more about how the brain works, and then how you can use it's kind of magic, your mind to control the world. With Dr. Justin Sanchez, he's a program manager at the Biological Technologies Office at DARPA, the Defense Advanced Research Projects Agency. Joining me, because I knew I couldn't do this on my own, Marc Pelletier from the Futures in Biotech show. It's great to have you helping out here.
Thank you. I'm hanging on by a thread myself.
It's fascinating stuff.
I'd love to ask Justin a little bit about some of the more forward or future uses. Like there's the program, the NIA and the CT2WS, the Cognitive Technology Threat Warning System. These are some of the things that you guys are doing right now that are pretty amazing. But also, Leo, you had mentioned that you were interested in getting an understanding how you interpret those initial signals. So there's so many questions here that could fill probably 5 hours.
Well, I'm going to let you take that future question, Justin, because that is fascinating. I'll tell you what the geeks watching want, and I want virtual reality, but I don't want to have to wear a helmet.
Right.
Yes.
Can I experience the world through a neural interface?
Absolutely. You absolutely can. And, your intent could be expressed through your neural activity through devices. your sensory system could be stimulated via these kinds of devices. So, we can honestly say that, these kinds of things are possible.
It's amazing. I mean, really, if you think about it, we don't experience the world directly as it is.
Right.
Impulses come into various sensors, the 5 senses, and by the way, in many cases, certainly with the eyes, look nothing like what we eventually sense. Our brain does a lot of work on it, interprets it, turns images upside down, does all sorts of things, and then we kind of think we are seeing the world. But it's a very much an interpreted understanding of what our senses are picking up. I could see that it wouldn't be that difficult to eliminate the sensorium and create, stimulate the brain directly. Is that how it would work?
That's exactly how it would work. And you really hit it, when you say that, yes, traditionally our bodies are the transducers for that kind of information. But, today the conversation is very different. We have devices that could, interface directly with your brain, to give that kind of sensory information back. Now, it's interesting that, one of the very early forefathers of the internet, his name was J.C.R. Licklider. Some of you may have heard of this person. Yeah. But he had a very interesting view of what he called brain-machine symbiosis. And back in his time, in the 60s, he kind of envisioned a future where machines and humans would be interacting in a very intimate kind of a way. And today, kind of back to learning that neural code or learning how to interact with the environment in the way that we are talking about, that's one of the ways that we can learn, how these signals emerge and how they give rise to function. Today, I would say that one of the challenges, though, is still developing the infrastructure and the computing architectures in order to do these kinds of things. But again, it's something I'm working on. So let's kind of get down to a very simple example. Think about your thermostat control. Okay, so over the years, thermostats have come a long way, right? You've had the old mechanical switch thermostat. That didn't work very well. In the 80s, we kind of came up with programmable thermostats. That works a little bit better. And then today we have things like, the learning thermostats that learn through interaction, right? As you turn it up or you turn it down, it kind of learns how to optimize the set temperature for, what you're doing throughout the day. It's not a huge leap to say, think of those learning thermostats, but instead of being driven by your hand turning them up or down, but being driven by your physiological signals. So as the thermostat adjusts the temperature and your body responds to that, there's information that is being encoded in those dynamical changes, right? The time varying changes. And if you develop some mathematics, you may be able to learn what those changes mean and re-inject them back into your machine in order to make the situation as best for you. So it's really kind of tailoring the machine for your own physiology, and you can learn it through that interaction. Now, while that's a very simple kind of example, just kind of take that mental leap and say, look, if I can do that for temperature, what if I can do that for cognitive function or memory or movement or interacting with any number of devices that are part of the Internet of Things these days, right? So that's why, back to that question, why now? We're starting to have all of these pieces at the right time to do this.
We talked quite a bit about the concept of neuroprosthetics. A way to restore function, either or maybe slightly enhance it in the present time. But what about really moving the human performance through interaction with computers leaps and bounds ahead? I mean, if you could interface with a really powerful image processing software, but then use parts of the brain that you're not necessarily using all the time to go and recognize certain elements. So I read something about your neurotechnology for intelligence analysis program, neurotechnology for intelligence analysts, where analysts are sitting at computers combing through warlike data where you're trying to look for targets, but you then don't even have to, there's so much imaging information coming from satellites, whereas you just have an analyst sit and look at it, and if he kind of recognizes something, then it puts a bookmark on that piece of information without you actually having to think, okay, I'm going to stop. That's a possible site, where you're just looking, and then the computer recognizes certain synaptic activities and then marks it without you having to consciously think.
Without a doubt, there are things that computers do very well, and there are things that biology does very well. And traditionally, right, throughout all of human history, the development of those two things has really been separate, right? People try to make computers smarter, or computers as good as they can possibly be. People are trying to, affect biology, make biology as good as it can be. But, again, today, I think the conversation that we're having is very different. It's more of a question of how do we get the best of biology and how do we get the best of computing and put them together in an intelligent way that we have a mutualistic benefit. And again, now is the opportunity to start building the technology to do these kinds of things. And, again, we're starting to see glimmers of that in wearable technologies, in new computing platforms that give feedback, in direct neural interfaces. And what I really think it's going to take is the innovators out there to recognize where those key pivot points are and start developing the technology for everyday life that, we can really benefit from.
Okay, this may be a sensitive question. You can blow me off if it is. But here you are, you're working for the Department of Defense. And I always think about, well, what is the interest of the Department of Defense in this? And you've made a good case that one of them is to take care of our wounded warriors. And that's a really, really, really good reason to do this, if you don't need another reason. But are you concerned that this might be used for drone pilots to control drones, or as you just explained, to analyze military data, analyze satellite data? Are you worried about the militarization of these techniques?
I mean, we think of all of those questions up front. Even at the start, the inception of our programs, we seek input from people on a panel that we call the Ethical, Legal, and Social Implications panel. And they provide insights and knowledge about these really hard questions. And at the end of the day, they are hard questions, right? This is uncharted territory. But again, this is the mission of our agency, is to seek out, these areas, to know the most about these areas that we can, so that we're never surprised by them. So it's very much an issue of, we know they're hard questions, we recognize that, but let's go after them in a way that enables us to really be informed and look at those questions head on. Every technology has primary and secondary uses. I mean, you can name anything. And these technologies are no different from that. So we have to handle them with great care and great insight, and that's exactly what we're doing.
That's really encouraging that step is taken. That's the first step. I'm really glad to hear that. And then the second question is, how does this make its way into the rest of the world, or the rest of the United States, or us, as a practical something that we can use? How does this migrate out of the research lab?
Yeah, another great question. So one thing we haven't talked about on this interview is who actually works on DARPA projects. So we have academic institutions, we have small and large businesses working on them. We have national laboratories working on them. And again, these problems are so difficult, they're so DARPA hard, that no one organization can really go after it alone. So all the teams that are working on the programs that we just talked about today, all these prosthetics programs, they consist of variants of those three groups that we just talked about. And the great thing about those groups is that within the course of 4 or 5 years, this is the duration of these programs, the milestones at the end of this are to produce medical devices.
Great.
So produce medical devices that can go through, let's say, phase 1 FDA kinds of trials, or go through kind of pivotal trials at the FDA. So it's our hope that, we not only show proof of concept of these kinds of devices, but they'll also make their way into the clinic so the broader aspects of society can ultimately use them. And we've got one great example of this that's already happened. So we've developed this one prosthetic arm. It's called the DECA arm. And for those of you who don't know who DECA is, this is Dean Kamen, the inventor of the Segway.
Yeah.
He actually developed one of our prosthetic limbs. And on that project, we said, look, we want the world's most advanced prosthetic limb that has near natural, size, weight, shape, grip strength. And it went from a concept all the way to FDA approval over the course of a handful of years, 5-6 years. And that's an example of it on the screen there. So we're working really hard to take that technology, which is FDA approved, try to make it accessible to people that can prescribe them to anybody living with amputation. And really get the benefit of a DARPA investment, an investment of the public's dollar back for a technology that can really change somebody's life. That arm is really remarkable.
Super exciting. They call it Luke after Luke, for obvious reasons.
Skywalker arm.
The translation potential is enormous, and ever since the 50s when DARPA was set up, we're living today in a technology helped move forward in part by DARPA.
Hey, Marc, real quick on that point. So, the internet, GPS, night vision goggles, those are just a few of the things, right?
So take the smartphone, for example. When Steve Jobs says it's a phone, it's the internet, it's an iPod. Everybody thought, well, great, it's the phone, it's the internet, it's the iPod, all three. But really, it was the internet that I think became the new platform of computing, and it changed computing into this new post-PC era where we're now carrying around mobile devices for having the internet in your pocket. And so we've kind of hit a singularity. Those that don't carry around the internet in their pocket don't have access to infinite knowledge at all times. So we've transformed to a point where, I don't know, Leo, can you live without your smartphone?
No. And if you think about it in a way, that's a prosthetic device, isn't it? I mean, it extends the human mind beyond our immediate locale.
With the incredible potential of interfacing with the computer through thought and not through standard interface, where you could have computers doing all kinds of functions where you're integrated with the sort of the system level information that the computer does well that you don't necessarily do well. Do you think, Justin, there'll be a time when there's a singularity where everybody's going to want a brain-machine interface implant, helping us navigate through these improved performances, human performances?
I don't know if there'll be a singularity event like a lot of the technologists talk about. I view this more as, humans have always been changing their interaction with tools, right? And, the internet, smartphones, computers, it's a different kind of tool, right? But nonetheless, it's a tool that's becoming more integrated in our lives. It's a tool that's becoming more integrated with our physiology. And, we're going to continue to try to get the most out of those tools so that we can live the best lives that we ultimately want to live. So I think that there'll be a natural progression here. I don't think that there'll just be one kind of event that will make all of this happen. I think it is happening right now before our eyes. So
there's no watershed moment where it's going to cross over.
Yeah.
Could it be when musicians use
Marc,
this?
he's got it in the lab. He just can't talk about it.
I know, I want it. I'm going to visit him.
In fact, he might even be an artificial intelligence. No, I'm just teasing.
Decent. Good job.
We've all seen Terminator too many times. Clearly, that's part of the problem. We're going to take a break. We're talking to Dr. Justin Sanchez. He's program manager at DARPA's BTO, Biological Technologies office. I like outfit better. You call it the outfit. And really fascinating stuff. And, of course, your research at Miami is also very much around this subject. Do you get to do research much anymore, or are you managing a bunch of people doing the research now?
Yeah. So these days I'm 100%, at DARPA and just doing that. I don't get to do lab work anymore. But there was a time in my life, again, it was fantastic, going through that experience and working on the nuts and bolts on building these kinds of devices.
And yet, you're making such a huge difference. And that's what I can understand that while Marc and I, as avid science fiction readers, are thinking about the amazing things that can happen, really, you can see immediate impact in prosthetics, in curing Alzheimer's and Parkinson's, and that are just really very important to the individuals involved and make a massive difference in people's lives. And I think that's probably got to be very satisfying. We're going to get some... Yeah, I'll let you talk about it. We're going to get some final thoughts in just a second. Marc Pelletier is here, my old buddy from Futures in Biotech. You can see he's in his lab. Or is that just a dummy microscope that you just put there for the show?
It's a cell culture.
You got something going right there? Right
good.
Now, there's something growing?
No, it's an incubator.
Yeah.
Humans. There's a few humans in the incubator.
I want one.
Fun.
You know, the one thing I miss about doing the show is just the amazing things we hear about that we are living in amazing times. And things are changing so rapidly. The Genome Project changed so much. And when we did the show, 5-6 years ago, that's what we were talking a lot about. I feel like this is the next thing.
I maybe might be able to announce something in a couple of weeks that
boy.
Be a game changer, I think, in terms of genetics.
That's exciting.
This is something that's coming out of Harvard that I've been working on acquiring and to commercialize. And if so, it could change. It could be a pivotal moment, I think, in history. Right?
They never accepted me into the Personal Genome Project. I just wanted to let you know.
I know. I fought so hard. I was, George, get it done.
What's wrong with my genome?
You could have. Yours would have been great because you could talk about it, and you were willing to get it up and get.
And I was going to pay for it and everything.
And get the word out to millions of people. Yeah. Millions.
My kids weren't as enthusiastic. They said, "Dad, you're sharing our genome."
Yeah, but there's enough of their mothers in there that it turns it all
just me. It's just me. Our show today brought to you by a very brainy sponsor, Braintree. We know you love Braintree. And you may say, wait a minute, I never heard of them. Oh, no, you've used them, my friends. You've used them. If you're a mobile app developer looking for an incredibly simple but very wonderful payment solution, you got to check out BraintreePayments.com/triangulation. If you've ever stepped out of Uber and marveled at, wow, I just got a cab ride and I didn't pay for it. That's Braintree. Ever stepped out of a Lyft? That's Braintree. Airbnb, StubHub, Hotels Tonight. That's Braintree. Braintree makes it easy for these apps for you to make it a great experience, because of their one-touch pay solutions, the end-to-end integration of things like Apple Pay, PayPal, credit cards, Venmo, Bitcoin, all with 10 lines of code. If you're a mobile app developer, don't make that mistake of trying to develop your own secure payment solution. 70% of customers leave a site at the shopping cart before checking out because they don't trust it, because it's too complicated, because they don't get it. Braintree solves that. It solves mobile cart abandonment by offering the best-in-class mobile checkout experience. And you know that because you've used it. I think people sometimes use Uber don't even know they've used it. It's like, I can't believe it. I got a ride and then I got out of the car and I didn't have to do anything. BraintreePayments.com/triangulation. You can go there right now, sign up for their V.0 SDK, try it in the sandbox at no cost to you, see how it would look in your app. They've got great support too. But you know what? This is so simple and works with all the languages you work with. You're going to love this. And one more thing, just to sweeten the pot, your first $50,000 in transactions, fee-free. That'll get you started. BraintreePayments.com/triangulation. Don't do this yourself. Use the best. Their one-touch integration is so sweet. Customers love it. You'll love it too. BraintreePayments.com/triangulation. We're talking about, as we often do on Triangulation, the future, but this is the near future, a future that's happening right now thanks to amazing researchers all over the country, all over the world, and Dr. Justin Sanchez at the Biological Technologies Office of the Defense Advanced Research Projects Agency, DARPA. They're the folks, as he mentioned, who gave us the internet and GPS and autonomous vehicles, and they're going to give us robots and mind-machine interfaces. That phrase even is kind of boggling. That's really something science fiction loves, is the idea. But I don't know. I wonder, and I've asked it, but let me ask it directly. How do we learn the language of the brain in such a way that we can get a machine to understand it?
Yeah. The first step, again, this is how it's been done in the past, is that you'll record some brain activity and you'll have somebody perform some kind of behavior
You just
task.
watch it.
And watch it, and you say, okay, what lights up in the brain? What neurons start firing when you're doing this task? And what you ultimately do is you build some mathematics or computer code that correlates those two things. They relate those two pieces of information. And once you have that relationship, you can expand the things that you ultimately do. So in the case of, again, movement, there may be some neurons that move or that fire when you move in a particular direction, and other neurons that fire in a different way when you move in the other direction. Again, once you have that fundamental relationship, you can apply it to a wide variety of scenarios.
And MRIs are a good enough way to measure this? There's enough resolution, enough detail coming from those?
MRIs are not. So again, you can kind of see where blurry areas of activation are via MRI. And the other thing is that there's a problem with MRIs. You're stuck in this tube, right? And laying in this gigantic magnet. So one of the reasons why DARPA is doing this kind of work is we say, look, that's not good enough, right? If we really want to do this, we got to do it a different way. So we needed to develop those technologies that can go to the individual neurons, which MRI cannot access, and say, look, I need to read that information. I need to be able to correlate it to some kind of function, whether it's memory or movement or whatever it may be. And then once we understand that functional relationship, we build it into software and computing platforms to use it for a wide variety of behaviors.
We talked to Dr. Michio Kaku about his book, The Future of the Mind. And that's one of the things he's talking about, of course. And he says you can read dreams at this point. You can actually see images on a screen from brain activity.
Yeah, there were some recent studies where people were doing neural recordings while people were sleeping to see what kind of activity was there, and trying to again read out that information.
Incredible.
So again, that comes back to that neural code of if we are able to observe it and relate it back to something in the environment, then we can find that correlation, and it will tell us how that how thoughts get translated into action.
Where are we in this? We're at a pretty primitive stage still.
Very primitive, especially for humans. Again, up until a few years ago, we really did not have the ability to record this kind of activity in human subjects. Most of the work that was being done was in kind of laboratory environments, and couldn't even observe these kinds of things. So, this is a really critical point where we have that access to that information, and we're starting to understand it.
One thing we know from the DARPA Grand Challenge 11 years ago. My friend Patrick Norton was down there covering it for the screensavers.
Oh, yeah,
and he almost got hit by a autonomous vehicle that had no idea what the road was.
Right.
And 11 years later, we're saying, oh, you know what, these are much better drivers than humans. We got,
right.
That's 11 years.
It's only 11 years, right? And the same holds true for the robotics challenge. So many of you probably saw the blooper reel with all the robots falling over and things like that. Give that another 11 years or so, and I'm sure there's going to be remarkable robots. And I would say the same is going to hold true right now for interfaces to the brain. Right now, we're just taking our first few steps on this and understanding how those circuits work. And, give it another 10 years, and I'm sure it's going to be a much different world.
Wow.
Moore's law in the development of the CPU is switched over to same level of power or same level of CPU power, but consuming less power. And it seems to be reaching a plateau, but it doesn't mean all technology is reaching a plateau. The genome cost $1 billion in 2000, and now you can sequence it for under $1,000 on a bench in an hour.
And that happens so fast.
Right. So that's 12, 15 years.
Yeah.
So I think Justin's field is one of those that could have a logarithmic growth, or we're currently in that logarithmic growth. That patient that you had in the not the wheelchair, but the sort of the wheel bed, she was moving an arm around and she had a prosthetic interface or a brain machine interface that looked like very much what we'd classically call a prototype in any kind of development lab. Do you see that turning into a small implantable chip sometime in the near future? How long is it going to take before that can be implanted without having an interface and it go wireless?
Yeah, So all of our new programs now, the device constraints or the requirements on that are all fully implantable, miniaturized kinds of devices. So we already have prototypes within the last year for exactly what you're talking about. Self-contained, wireless, onboard processor, onboard rechargeable batteries, all of these kinds of things. So yeah, even since those videos that we just looked at, the field has evolved tremendously.
How soon before that kind of thing is common? That won't be commonplace, but it'll be beyond prototype. It'll be something that you could conceivably get.
Yeah. So with those prototypes, we're going to have to go to the FDA, the regulatory agencies. They'll have to take a look at them to make sure that those devices are, safe and effective and all of those kinds of things. And the time frame for that is on the order of 4 or 5 years.
That's great.
I see a problem. Sorry to hit a problem. So for patients that are trying to restore function, the FDA would be absolutely fine. But would the FDA ever approve something for enhanced performance?
Yeah, that's a good question, and that's a road that not very many people have gone down yet. Where I really think that that's going to take place is back to this kind of wearables trajectory, right? Okay. People are starting to use wearables in a wide variety of ways. Those may get integrated into everyday life in a much deeper kind of a way, and I think things will stem from that. So that trajectory will likely intersect with the whole medical side of the fully implantable kinds of devices.
If I got my wireless microarray,
I'm ready. Give it to me.
I get 1,024 electrodes, and you've picked all the great neurons. That's probably all of them. and then that would be great. But removing it, could it cause any kind of emotional trauma because I'm no longer superpowered, or would it be this is just so much fun, or does it cause any physical damage to remove the electrode from the brain if somebody wanted to take it out?
Yeah, so all of these technologies are reversible. That's a good thing, right? I mean, we're building on technologies like deep brain stimulators that they're classified as reversible kinds of medical treatments. So all of the people that have been implanted with these kinds of devices thus far, not only DBS, but also the ones that we're talking about on this show, the ones that have been removed, everything has been fine. They've gone back to their normal lives, and again, that's a great part of these technologies. They're not permanent in that regard.
I love this idea that not only would you be able to pick up a cup, but you might even be able to feel it. There's an article on the DARPA site about a company called Haptics that is working on providing prosthetic hands with a sense of touch, which is remarkable. What is going on here? And I am, it's so tempting to think about the sci-fi of it, but there's so many people who will benefit immediately from these technologies. It's such a difference that you're making soon, like right now.
I can't let go of the sci-fi because it's just so compelling.
I know.
You take a drink of a lousy cup of coffee, but then
if you were missing your arm, Marc Pelletier, you would be very, very happy to hear about this research and how close this is to making a prosthetic you just think.
Leo, just one point on that. Again, DARPA is part of the DoD. One of the things that I get to do in Washington is I get to meet with military personnel that have suffered great injury in protecting our nation, and to try to repay some of that debt using these kinds of technologies is really what we're after.
Yeah.
Again, when I see military personnel using some of our technology and them getting a benefit from it, again, it's really remarkable. And I really encourage people, if you don't know somebody who has been in the service and again made that huge sacrifice, go out and try to meet some of these people and understand what kind of needs that they're under, and anything that we can do to try to give them a better life after they've lived in that line of service is something I've really dedicated my life to.
Absolutely.
Don't let me undermine my fascination with sci-fi.
No, we love it. I love it too.
That chocolate must have been the best chocolate of her life.
No kidding.
Because it was a chocolate that she's been wanting to be able to eat herself. And that is Marc, humbling.
To your point, Marc, again, the mission of the agency is to push the frontiers and the boundaries. So, what's fascinating about these programs and this opportunity is that we get to do both.
Yep.
Right? We
Right,
get to not
exactly.
only try to help people, but also push the forefront of science and technology for the brain. And to me, again, it's a once in a lifetime kind of experience.
Yeah. Let me just play this little clip from this year's State of the Union address, which kind of puts it into a context.
Creating revolutionary prosthetics so that a veteran who gave his arms for his country can play catch with his kids again.
That's pretty much all you
Pushing
need.
out
That's all you
into the
need,
solar
baby.
system.
Hey, I
And,
want to thank
just
you.
A note there, that arm that is in that picture, that
Yeah.
was developed by DARPA.
Yeah, I know. I want to thank you for the work you're doing, Dr. Sanchez. This is so important. It makes such a difference. And if you'll forgive me, I love it that scratching this itch, and then we're talking literally being able to scratch an itch, can actually propel us into this very fascinating future that Marc Pelletier and I are both looking forward to, where we could just jack in and our sensorium expands just as the internet has expanded our knowledge base. Thank you so much for being here. I really appreciate it.
Thanks so much for having me on. It was a great experience.
Really interesting stuff.
Thank you,
Justin
Justin.
Sanchez, he's a program manager at the Biological Technologies Office of the DARPA, of the Defense Advanced Research Projects Agency. Thank you, Dr. Sanchez. And Marc, thank you for setting this up, because Marc's always brought us some of the most interesting guests for years and years and years, first in futures in biotech and now. And I thank you so much. And I'm very excited by what you're up to. Everybody should find out about Marc's incredible work soon at Aeromics. And you know what? As somebody who is looking forward to my first stroke, I'm very glad that you were working
there
hard
for
on
you.
this.
We have to get it before my first stroke.
Okay. I'm
approval.
almost 60, so you gotta hurry here. You gotta hurry, okay?
Will do, sir.
Thank you. Great to see you again, Marc. I really appreciate it.
you.
Take care. We thank all of you for joining us. We do Triangulation every Monday, and it's always an eye-opener. It's always a mind-bender. I love that. I love expanding our horizons, and I'm glad you're here to do it with me. Please join us each Monday morning, 11 a.m. Pacific, 2 p.m. Eastern Time, 1800 UTC, or watch on demand, because, every show we do here we make available on the internet on twit.tv/TRI. That's the web page. But you can also find it, because we've been around for a while, on every one of the podcast platforms like iTunes and Xbox Music and the podcast app on your mobile device. There are great Twit apps on every single platform. Look for those. You can even subscribe on your TiVo and your Stitcher and your Slacker and your Spotify. We're even on Spotify now. So however you get it, don't miss an episode, because it always makes me feel really good to start the week this way. Thanks for joining us. We'll see you next time on Triangulation. Bye-bye.